Okay, so now we know the selection rules for Raman and infrared spectroscopy and whether or not a given normal mode, once you know its symmetry, will or will not be active. But how do you find the normal modes in the first place? Okay, so that's what we're going to talk about in this video. There's a little bit of math in order to do this, and it follows this protocol, which I'm just going to tell you what the protocol is. Um, you know, a lot of things we just don't have time in this course since it's such a broad course. And there's so many different things to cover. Inorganic chemistry is a huge field. We just don't have time to go into the derivation. But I can always tell you it offline if you are, really have a desire to know. So what we're going to do is we're going to determine the number of stationary atoms, and we're going to assign that a representation. So we're going to call that gamma stationary. Remember, gamma just means kind of any representation, could be reducible or irreducible. And then we're going to determine how the vectors x, y, and z transform, remembering that we are always defining our z-axis as being collinear with the principal rotation axis, okay? So remember, the principal rotation axis was the rotation axis with the highest order n value. So like usually maybe like a C4, that's kind of a high n value, or a C6, right? So we're going to call that transformation, we're going to call that representation for how the vectors x, y, and z transform as gamma x, y, z. And then we're going to find out what something we're going to call gamma nuclear is. That's going to be just determined by multiplying gamma stationary by gamma x, y, z. And what gamma nuclear represents is basically all the different ways that the atoms can move within the symmetry space that's compatible with symmetry. And so this includes stretches. This includes bends, right? The only two vibrational modes on a fundamental level that exist. But it also includes rotations and just translations in space. And because it includes rotations and translations in space, and those aren't normal modes, that's not a vibration anymore. That's a rotation or just a translation. We got to subtract those off if we just care about the normal modes. So that's the last step. So very abstract right now. It'll get more clear in a second here as we do some examples. Okay, so let's do it for water. Normal modes of water. So we have this formula: gamma nuclear equals gamma stationary times gamma xyz. And what we need to do first is define our axis system. So remember, our axis system is going to be, the z is going to be collinear with the principal rotation axis. Principal rotation axis for water is a C2. It goes right through the oxygen. Remember, water is in the point group C2V. C2V point group has 4 different symmetry operations. Okay, it has an identity operation, a C2 that spins the water molecule like this, interconverting the hydrogen, and then it has 2 different mirror planes. So this is going to be our z-axis, and we're going to put parallel z-axes on the other atoms as well, just labeling them Z1, Z2, Z3. And then what we're going to do is we're going to define x and y. And x and y you can define however you want. It turns out it doesn't matter. If we flipped x and y here, we get the same answer. But z you have to get right because the character tables are all set up assuming that you use z. And if you don't, you'll get screwed up. Okay, you'll get an answer that won't make sense. So what we then ask is, all right, we're going to figure out this gamma xyz. In this case first, you can figure out gamma stationary first, but it doesn't really matter. So what this is asking you to do is, what does the identity operation do? Okay, that's the first symmetry element in C2V. What does the identity element do to x, to y, and to z? Well, we know what it does. It does nothing. X goes to x, y goes to y, z goes to z. And so your character for this representation, your trace of your matrix, is going to be 3. Where did that come from? Remember, character tables and all this stuff are all about traces of matrices. So we have x going to x, y going to y, z going to z. Where did that come from? Effectively, what we did is we wrote a matrix that looked like this. This is the identity matrix, remember? Okay, we wrote a matrix that looked like this. Okay, this was just me doing a shorthand of it because you don't really have to write out this matrix once you start seeing the patterns. Okay, we wrote out this matrix. Okay, we're asked what matrix takes XYZ into XYZ. Well, it's the identity root matrix, one's on the diagonals. And then what's the trace? What's the character of that? Well, you take the sum along the diagonals, 1 plus 1 plus 1, that equals 3. That's why we're putting a 3 down here for gamma XYZ. Okay? For C2, what's going to happen when we do C2? Well, same thing. We're asking what happens to X, what happens to Y, what happens to Z. Well, if you have an X vector, okay, imagine you have an X vector right here. I should say, we're only actually looking for this XYZ at X1, Y1, and Z1. Okay, we're only looking at the central atom. So this gamma XYZ is for the central atom. So remember that. Okay, so it's for the central atom. So if you have an X vector, what's going to happen when we do a 180-degree rotation? Well, that X vector is going to go backwards, right? It's going to spin 180 degrees. It's going to go into negative X. It goes to negative X. Y, what's going to happen to Y? Well, Y is pointing this way, and now it's spinning, so it's going that way. So same thing. Okay, Y is going to go to negative Y. What about Z? Well, you're spinning along the Z. So if you spin along the Z 180 degrees, the Z actually doesn't change, right? You started with the Z vector like that. Yes, the XY plane shifted 180 degrees, but Z doesn't. So Z went to Z. So what your matrix is going to look like is the following. Negative 1, 0, 0, because X is going to negative 1. Okay, this is times X times Y times Z. And then 0, negative 1, 0, and then 0, 0, 1, right? And so this is negative X, negative Y, Z. That is the matrix that takes X, Y, Z into negative X, negative Y, Z. That is what the C2 representation is. So if we sum up the characters there along that diagonal, negative 1 plus negative 1 plus 1 equals negative 1. So you can hopefully see at this point that you don't really have to write this matrix out. You can just see it, right? Okay, I got a negative there, and a 1. Negative 1 plus negative 1 plus 1 gets me a negative 1. All right, so that's why I put a negative 1 here. So I'm not going to write the matrices out for the next two mirror plane ones. Here's a mirror plane in the XZ plane. So let's draw that out. It's a mirror plane like this. Okay, again, remember this gamma XYZ business is all around the central atom. So what's going to happen here? Well, an X vector. If we have an X vector, well, that's an X vector is right there. That's in the XZ plane. That's not going to move. The Y vector, though, is, right? Things on the right are going to get to the left. Things on the left are going to go to the right. The mirror plane is like this. You're going from here to here, hopping across the mirror plane, right? So Y is going to go to negative Y. Z is in the XZ plane, so that's going to go to Z. So we have a 1, a negative 1, and a 1. So 1 plus negative 1 plus 1, again, doing that matrix in our head, is equal to 1. So we put down a character of 1. Now we have the YZ plane. YZ plane, very similar to the XZ plane, but now it's the X vector that moves. Things in the front go to the back. Things in the back go to the front. So X is going to go to negative X. Y is in the YZ plane, so it doesn't move. Y goes to Y. And Z is in the YZ plane, so it doesn't move. Z goes to Z. So we have a negative 1, a 1, and a 1. Add those up together, we get a 1. And there's our gamma XYZ. We're done. Now we're going to come up with gamma stationary. And that's the second row here. And this one's pretty straightforward. All you're asking yourself here is how many atoms stay stationary when I do the transformation. So if I do an identity, well, both hydrogens and the oxygen don't move, right? Identity just takes it to itself. If I do a C2, what happens? C2, oxygen stays the same, but the hydrogens change places, right? So that's going to be 1. Only the oxygen. Right? I'll put in parentheses oxygen. What about gamma XZ? Gamma XZ is cutting the molecule like this, and there's your water. It's cutting in half. So the hydrogens are going to flip, but your oxygen is going to stay the same. So oxygen doesn't move. And then for sigma YZ, that's in the plane of the molecule. So that's a big mirror plane like this, right? It's a flat molecule from this standpoint. So nothing's gonna, you're cutting the atoms in half. So fine, the top half of the, or the front half of the atom is gonna go in the back half of the atom, but in the back half of the atom is gonna go in the front half of the atom. But atoms are just spheres, so that doesn't do anything. Okay, so all of these, the H's and the O's, are going to stay the same. Okay, so that's gamma stationary. Then the gamma nuclear formula tells you to multiply these together. So you got 3 times 3 is 9, negative 1 times 1 is negative 1, 1 times 1 is 1, 1 times 3 is 3. All right, at this point, what you have to do is you have to subtract off. Well, let's not do that. Let's first reduce this, okay? So there is a reducing representation formula that is described in your book that you can reference if you want. What we did in a previous video is we just said we're going to use guess and check, and that for the purposes of this course, I'm always just going to make the problems easy enough that you can use guess and check. But I can refer you to a lecture video I made for my graduate level course if you're really curious about how to use that formula. So how do we get this 3A1, 3A2, 2B1, 3B2? That was just guess and check, right? So if you go, that's the simpler way at least. So if you go 3 times 1, 1, 1, 1, right? That's going to get you 3, 3, 3, 3. That's A1. Let's just check this. A2, there's only one A2 we're adding here. That's 1, 1, negative 1, negative 1. Okay. And then what do we have? 2B1. So I'm going to times by 2 times B1 there. 2, negative 2, 2, negative 2. And then I have 3B2. So that's 3, negative 3, negative 3, and 3. And so hopefully when I add this up, this all works. 3 plus 1 is 4, plus 2, 6, plus 3 is 9. Okay, that's off to a good start. 3 plus 1 is 4, minus 2 is 2, minus 3 is negative 1. Looks like it's working. 3 minus 1 is 2, plus 2 is 4, minus 3 is positive 1. 3 minus 1 is 2, minus 2 is 0, plus 3 is 3. So that's work. So that's just proving to you, that this is the correct decomposition of this reducible representation. All right, so how do we then get, this is gamma nuclear. How do we then get the normal modes, right? That's what we care about. Remember I said that the gamma nuclear is all of the different all of the different degrees of freedom. It includes translational and vibrational, okay? So what we have to do is we have to look at the C2V character table, okay? And if we do that, let me pull that up, C2V here. C2V character table, we have to look for translations. So translations are the X, Y, and Z functions. Okay, it's translating in the X direction, translating in the Y direction, translating in the Z direction. So our gamma trans is going to be A1 plus B1 plus B2. And then we also have to subtract off rotations. Those are given by these rotation functions. Rotation in the X, rotation Y, rotation Z. And so we can call it gamma rot if you want. And that's going to be equal to A2 plus B1 plus B2. So we're going to subtract both of those off our gamma nuclear. Okay? So, oops, here we go. So gamma trans, remembering from the previous slide, was A1 plus B1 plus B2. And gamma rot was A2 plus B1 plus B2. So if we subtract those off, we're going to get our final answer, which is gamma normal. Let's put gamma norm here. So let's see, we have 3A1 minus 1A1. So that's going to get us 2A1. Okay. And then the A2s go away, A2 minus A2. 2B1 minus B1 minus B1, those go away. 3B2 minus B2 minus B2. So we're going to be left with 1B1 there. So normal modes are going to be equal to 2A1 and 1B1, okay? So that means we have 3 normal modes, 3 modes. All right, so what are they? Here they are. This should say gamma normal. So they look like this. And you can figure out what these are through other ways, but there they are. We have 2 of the symmetry A1. There's a symmetric bend. One of them is a symmetric bend. You can see that looking very symmetric. The other one is a symmetric stretch, and the other one is a asymmetric stretch of B2 symmetry. So remember we said the A1s are the things that technically are like totally symmetric, so they're going to look very symmetric. Anything else is going to have some sort of asymmetry associated with it. And so, here is that written out for you, okay? 2A1 plus B2. So you have it for the slides. Total of 3 modes. Does that match our formula, 3n minus 6? This is a nonlinear molecule where n is the number of atoms. We have 3 atoms in water, 2 hydrogens, 1 oxygen. 3 times 3 minus 6 is 3. So 3 normal modes, and that is correct. Which ones are IR active and Raman active? Well, we look at the C2V character table, use our selection rules that we learned about in the previous video. And you can see that the IR active modes are A1, B1, and B2. Remember, because they have X, Y, and Z symmetry. And the Raman active ones are all of them. So that tells you, well, the only one that wasn't active for something was A2, was an IR active, and I don't have an A2. So that means all of them are both IR and Raman active, which is kind of interesting. All right, so what we're going to do in the last video is just go over how to figure out whether or not you have a stretch or a bend.